Hi everyone, thanks for joining my presentation today. This is called From Business to Bytecode, Executable Smart Contracts. My name is Greg Woodmeyer, and this is for Athabasca University, Computer Science 610, selected topics in software engineering. Some of the topics we're going to look at today, we're going to do some definitions, just a brief review of the literature that was covered, so basics of blockchain and smart contracts. Look at the steps on converting from like a human readable language to bytecode, some of the issues and challenges that were experienced, and then a quick conclusion. The definitions we're going to look at are blockchain, ledger, consensus protocol, smart contracts, and bytecode. So in blockchain, everybody's heard about this lately to do with cryptocurrencies, things like that, but what actually is it? It's quite literally a chain of blocks. Each block is a group of transactions that are logged to different nodes that are part of the network. And as those transactions are built up over a certain amount of time, they are grouped together, and then the cutoff happens, and we need to determine which of those blocks is going to be the definitive one that gets added to the chain and becomes part of the ledger. The ledger in this case is the actual blockchain. This is our distributed database of all of the items, all the transactions that are added, and this has a record of the time, the addresses, any other information depending on which blockchain it is, which is really where blockchain stands out. So the ledger is an immutable ledger or line of transactions. You can't go back and change any of them, we can't delete any of them or update them. The distributed database, the security side of that, allows us to have that distributed to various nodes. And with that, we are decentralizing the database so there isn't one individual owner or one central trust on who can add or hold this information. In the cases of the Bitcoin blockchain, there is a transaction block assembled approximately every 10 minutes. And while those transactions are being logged, the previous ones are being verified and distributed to all the different nodes. As you can guess, with this happening every approximately 10 minutes, the ledger itself begins to build in size. Currently with Bitcoin, it's about 150 gigabytes. So sorting out which of those nodes actually contains the transactions that are going to make it into the block is done through what's called the consensus protocol in blockchain, and that's exactly as it sounds. There's a protocol that takes a consensus from all the nodes that determine which of the main nodes that has been collecting the transactions is actually going to be the one that's written into the blockchain. That information is verified by their nodes and distributed out across the network. So looking separately at smart contracts, they are basically taking a legal contract, or one version of it is taking a legal contract and converting it into something that is written in code that is then executable on the blockchain. And there's some obvious benefits there as we've gone through the previous definitions. The contract itself is added to the blockchain. Anything that happens with that, any transactions are written to that immutable ledger that is permanently recorded. And as you can guess, there's things that come from that. Things like digital asset management is a big one, personal information management, and a lot of things around financial and banking, Internet of Things. A lot of different domains are looking at it for implementing their technology. And lastly, bytecode is the actual code that the smart contract um, is converted to before it is placed on the blockchain. So bytecode is looking at it, looks a lot like assembly language. You're doing pushes and pulls and working directly with variables that are almost at the flag or the register level. So we'll cover some of those topics as part of our literature review. Well, smart contracts in blockchain are a newer idea. There's already some implementations of it. Where we're seeing it are things like business transactions, where there's legal requirements and technical representation. A lot of times this is coming from large financial organizations that have these resources available on hand. And there's a lot of possibility for this to work its way into other domains. In some cases, though, there just isn't that same level of legal representation and technical development available to be able to mate the two of these together and be able to execute that smart contract. The natural language processing side, a couple of different solutions were looked at: the Stanford NLP, Open NLP, and the Python Natural Language Toolkit, or NLTK. The Python NTLK seem to be the best supported and also offered a lot of background where people are creating domain-specific languages and working with that inside of the natural language toolkit in order to decode sentences that have something to do with their domain. In this case, we're talking about what some of the authors have coined as legalese language to describe legal contracts. Going back to the first item, smart contracts and blockchain, I did mention the smart contract platform support. So not every blockchain was originally built to be able to handle smart contracts. The most popular one at the moment is known as Ethereum. There are some blockchains that are building their own smart contract management, and then there are others that have used or started with what Ethereum offers, and then what they're calling forking or splitting off of that and making changes to theirs to improve how those smart contracts are executed. An example of a couple of these, there's one called the Tronix blockchain, which, as described, is a fork of the Ethereum blockchain. Um, and all they've done there is change some of the underlying code so that they can increase the speed of the smart contracts and some of the options that they have. And the second one is known as Codius, which is a smart contract solution that was built on the Ripple blockchain, which is used by banking in some Asian markets. The next item considered is model-driven development or model-driven engineering. So these are available for executing code automatically based on a model that's created, whether it's a use case or a class diagram or whatever it is, as long as it is formatted or conforms to the Unified Model Language, or UML, for the foundation of the textual language. There's a number of IDEs that are set up to build those models and convert that directly into high-level code. These are known as meta models and can be used to convert into a number of higher-level programming languages. Again, a number of these were considered. However, two of the more supported ones popped up as Poseidon for UML, and that's a visual notation editor that allows conversion into Java and some of the C languages, or PyUML, which is Python UML, and it's a plugin for Eclipse that can handle both directions, so the diagram being converted into Python code or Python code being turned back into a diagram. At this point, there isn't much issue with getting information into a diagram and then into a high-level code. The problem is getting into high-level code that can be used somehow to then translate into a bytecode for the smart contract. Some of the more advanced work involved going from a high level like Java or C Sharp into a newer language known as Solidity, which is a web browser based IDE with code that's kind of based on C++ and Python, a mix of the two, and basically converts from that down into the bytecode, which we'll look at a little bit later. Now, getting into the actual work of going from business language to bytecode, there are a number of steps to look at. The first part is obviously what are we using for an example agreement, or what is the template going to be? A very common transaction that fits well with the idea of smart contracts and some of the benefits that they offer is a simple automobile sale. For the smart contract side, the minimal information is really just who's the seller and the buyer, which really that comes down to addresses for storing um, wallets or where currency gets moved to, the actual currency exchange itself, and then finally a change of ownership or transferring the asset between one person and another. Executing this as a smart contract means having both parties assent to the agreement itself, setting up their deposit addresses or withdrawal addresses, ensuring that the currency is available, and then ensuring the transfer of that digital asset. And this immediately is where you see the strength of the smart contract and the blockchain come together, where if the currency is not being exchanged, the digital asset isn't released, or if somebody tries to take the digital asset or do something fraudulent in this case, the blockchain cannot be changed, meaning that that asset doesn't move until there's been some kind of a contract executed on it or the owner of that has done a deliberate transfer. So what we're seeing happen here is we've got the natural language written out as a contract. We've imported that to our natural language processing toolkit, And we can see that the buyer agrees to transfer the full amount of a certain number of dollars to the seller in exchange for a particular asset. Running the toolkit on this, we were able to tokenize each of the words, so we're extracting that statement, and we're putting tags on each of them to represent items like nouns, verbs, and anything else relevant to building the actual line or this part of the agreement. In actuality, for this case, all we're looking at are some of the nouns. Again, we're looking for buyer, seller, the amount, and the digital asset. At this point, a class diagram could be created based on that information using Python UML, with the added benefit that we're able to do a round trip again here. So if we can get down to the bytecode level and we can somehow extract the information from that, whatever we have in this class diagram created by Python UML, we can put back into a natural language how we originally received that. As you can see, what was found from the natural language toolkit, it really only generated one class with a one-to-one in this case for a single asset and a single purchase. Both sides require an address, so one's a seller, one's a buyer, and in both cases we need to get and set addresses, and one needs to send a confirmation and one needs to receive a confirmation. Now again, a number of tools exist for taking a use case diagram or a class diagram and changing that into a high-level programming code. This was easily the most difficult part of the research and where a majority of the time was spent. As mentioned before, there were no direct available tools for getting from a use case or a class diagram into a high-level code that could be convert into Solidity, which oddly enough was titled UML to Solidity. So this is a plugin for Papyrus, which is a UML modeling option for the Eclipse IDE. There was a somewhat similar option that could have pursued on the Visual Studio IDE side, but there's still an amount of code that would have to be developed around that. And obviously the point of this research is to get from A to B, acting somewhat as an end user, or what an end user might experience at some point if there's an integration built into each of these steps. The Solidity code at the top of the screen there is just a very small subset of what was actually required to implement the described agreement of the vehicle sale. Some of it includes items for things like canceling the contract, hitting that escape loop, and putting the like reversing the transactions and any of the costs and transaction fees back if at some point it was canceled or there's some kind of an error with the smart contract, just due to say a bug in the programming. So from there, as mentioned previously, we need to convert down into the bytecode itself, so into the assembly language, and this was done through the web browser-based IDE, which was known as Remix for Solidity, which basically allowed us to copy the Solidity code directly into the browser IDE and run the conversion on it. Again, this is a very, very small subset. This was about probably 20 times as long once it was turned into assembly code. But at this point, just even with the screenshot here, you can see the level of coding that goes into it and the information that's being passed back and forth. So after all of that work, what it all comes down to, what we're left with is the object, and what you're seeing is the hexadecimal bytecode as it exists and what you would see on the blockchain itself if you were looking at the individual transactions. For the research, the only thing I wasn't 100% able to do was test that the smart contract was able to execute as it is. I didn't have the ability to set up the whole Ethereum, like both sides of the contract on the production blockchain, the one that everybody uses. There are options to set up your own virtual blockchain and be able to test it that way in your Ethereum virtual machine. But I had a number of challenges getting that working as expected. So I got down to the object level code. Everything else appeared to execute correctly, and at this point I don't have any reason to believe that the object code wouldn't have been accepted by the blockchain. A pretty ambitious part of this research was getting to this point, but then also looking at, is there a way to get it back out of the object code or the assembly to bring it back up to a natural language? Because part of the reason for doing this is if a smart contract gets called into question and there's any kind of arbitration around it, the original contract itself needs to be viewed. If there's something signed on paper, that's easy enough, but if there's something that was executed on a smart contract, there's nothing left now to extract out of that to say, here's what the original contract looked like. So at the time of this research, there is a project looking at reverse engineering this opcode into the original assembly, which can then be built up after that. And this is called porosity. It's not exactly as described, though. It's not going to do a direct conversion back because the context of the information has been lost. The syntax is still there, but unless you have the context of what the contract itself actually held, you're not going to be able to turn it back into the actual natural language that it was originally. So overall, the point to the research here was to try to get from what would be a natural language down into a bytecode that can be executed on the blockchain, and we were able to show that that could be done. This did require an amount of technical knowledge. So again, an end user wouldn't be able to go through these steps, but the technology exists, those solutions are there, and being able to build integration between these to go from one step to another, whether that's some kind of massive development setup that would allow you to get from one to the other, or if there's a package that just includes all these items in it that could take that a very generic legal contract, some kind of a templated contract even, and convert that down automatically into something that could be executed as a smart contract. So there are a number of challenges in smart contract automation. So let's describe the reverse engineering side of it. Unless you've built something very specific and you've kept the context information, which some people are looking at various ways of recording context in variables that get mixed in with the smart contract and put on the blockchain, could that be pulled back out of that? There is that option to store that in some kind of a natural text. That way, other people are looking at having two blockchains side by side, one that's going to hold the actual opcode, another one's going to hold the contextual information. Number of ways to do it. A lot of that's still being worked on. The reverse security side means that if we are able to reverse engineer the contract, we could reverse engineer the security. So there's a number of issues around securing the blockchain that way. The problem there is the overhead that goes into the additional steps of decrypting that information to verify the information going onto the blockchain, which again is the whole point in the way that the solution is set up. Alternatively, instead of trying to pull the information back out of the smart contract itself, being able to simply rewrite the contract and treat it like a checksum. So then do all the work on this and encode it back down and compare the end objects to see if they are equal is another way to determine if the contract had been executed correctly. And the last challenge is really around platform improvements. With blockchain being so new, there's updates coming out, there's changes to it. Anything that's done along those lines is likely to affect the contracts that have been currently executed on there. So now they're at this point where they can't do major updates to the smart contract language or how it's executed for the chances that there's going to be problems, experiences that are going to impact previously executed smart contracts. So really quickly here, as we're almost out of time, so related and future work. As mentioned earlier, a lot of the functionality I was able to extract out of the various platforms and solutions as I went could be integrated. There's already other forms of integration that exist between some IDEs and some of the tools that were used. So bringing that to the tools that were used in this exact case shouldn't be too difficult, but there's definitely development effort required there. The web-based builders, I think a lot of what was done here could be executed primarily web-based, especially with blockchain being a web-based platform. This could be executed, simulated, verified completely in a web-based browser with basically being able to enter in some kind of a contract line or language into a field and having your contract basically come out the other end as a smart contract. This may not be as automated as described, but with some end user programming, some minor things that could be done in there could be offloaded to the end user. There are a number of references used for this paper, but some of the key ones are here up on the page. And that's it for my presentation. Thanks for listening.